All right, so now we move to approximating area under this curve. All right, and so for the purpose of this discussion, let's just suppose. So when we talk about the area, we want to talk about the area of this region, right? And so in order for this to make sense and for the argument to go smoothly, we just suppose that f is positive or at least non-negative at every point on the interval AB. And we will be talking about the closed interval AB throughout this discussion on integrals. All right, so we are trying to we're interested in approximating and eventually finding the area under this curve. Okay, and as I said before, we are going to be using a bunch of rectangles to do this. So so that's the assumption, okay, because we can talk about the area above the x-axis under this curve f. Right, so the first thing we do is, as we did before, we are going to partition, that's a new word maybe, partition this closed interval AB into small subintervals. In fact, n subintervals. Okay, now in general, in order to define what is called the definite integral, which we will study more formally in the second section, we don't have to have each of these subintervals of the same length. Okay, but it is much easier, again, for the purposes of introducing these new ideas, if we make these subintervals all of the same length. So we are going to let n, let's say delta x, which is going to be the length of each subinterval, to be b minus a divided by n, right? So, well, that makes sense because the length is b minus a. If you divide this into n equal subintervals, each of these subintervals is going to have the length of delta x, which is b minus a over n, right? So this is called a regular, you don't need to really know this, but it's called a regular partition where each subinterval has the same length. All right, so that's a start. And also, maybe I should say, we are going to identify these things. So A and B, these are the endpoints, right? We will call this x naught, and then x1, and x2, and so on, until you have xn, right? So if you have, this is x1, this is x2, make sure you count and make sure you have enough subintervals here. In this picture, you have n subintervals, okay? And the right endpoint of each subinterval is x to the I, x sub I. So the second subinterval, for instance, the right-hand side, the right endpoint is x2. The 17th subinterval has the right endpoint, which is x17, and so on, right? I hope you can see that. Okay, so that's the regular partition where the distance between x1 and x2 and xi plus 1 is always going to be delta x. All right, so okay, so that's fine, right? Now, so how are we going to approximate this? All right, so what we will do, we're going to pick a representative point. And we're going to do this in maybe 2 or 3 different ways. I pick a representative point for each subinterval. Let's go ahead and denote this. So this representative point is going to be denoted with xi star. Okay, for each subinterval, and evaluate the function there. Okay, so what are we talking about? I'm going to show you. Oh, and then finally we add them. Add what? Add the areas of all n rectangles. Now, what rectangles are we talking about? Of course, you will see this in a moment, okay? And I'm going to go ahead and write down the total area, right? So each area is a rectangular region. The height is the value of the function at this representative point, which I haven't talked about yet. I will show you this, and I will show you mainly like 3 different ways of doing this. And then the base of each rectangle, as we said, is delta x, right? So you have delta x here, which is the same for every subinterval. So if you add all of these, okay, as I goes from 1 to n, because we have n subintervals, this is going to be a good approximation of the area under the curve. Okay, I hope it makes sense. And this exactly is Riemann's idea. And in fact, about 2,500 years ago, the Greek mathematician, philosopher called Archimedes had something very similar, a similar idea. And he called it the method of exhaustion, because he was exhausting this thing, or maybe because the process was very exhausting. All right, so I keep talking about these different ways of doing this. And so here's the first way. Let me go ahead and make a couple of graphs. Okay, so I have drawn 3 identical looking graphs here. This is A, this is B, the 2 endpoints. And so I'm going to, for the purpose, again, for convenience, I'm going to divide this interval AB into, partition this into 5 subintervals here, 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 here. Okay, so you have 5 subintervals. And for the first one, I am going to do this thing called left endpoint approximation. What do you think this is? Remember, I said we have this freedom to pick the representative point. So basically, it's a point that represents that each of these subintervals. And if we decide that the left endpoint of each subinterval is the representative point, then this is what's going to happen. I think I'm going to be able to do this. Let's see if I can do this with a different color for rectangle, and I tried to make this into a thin rectangle. So I am going to pick for this first rectangle, this height right here, okay? So 0 or A is the representative point for the first subinterval. And then my triangle is going to look like this. Okay. Is this clear? Maybe not clear. Maybe I will make it a little thicker. Right. So the first rectangle is going to look like this. All right, the second rectangle, for this second subinterval, I'm going to pick again the left endpoint, which is right here. So I evaluate the function, and we assume that this function is going to stay at that level for the entire second subinterval. For the third subinterval, the left point is here. So that's my third rectangle. For the fourth one, this is the left endpoint. So you evaluate the function at that left endpoint. That becomes the value of the function for this entire subinterval. And for the last one, that seems to be overlapping. Yeah, that. Okay. So you can see that's those are the 5 rectangles where each of the 5 subintervals is represented by or at the left endpoint. So this will be x1 star, x2 star, x3 star, x4 star, x5 star. Should I write this? Okay, you get the point here. Literally 5 points, right? And so these have been chosen. And so you can tell if you add up all the areas of the rectangles. So the first rectangle is actually an overestimate. This is very underestimated, right? Because this is less than the value of f at most of these points here. And so you can have an overestimation and underestimation. Maybe they'll balance out. Maybe it'll be pretty much the same as the real area under the curve, right? I'm not really sure, but it's only an approximation. Okay, so what happens if you have the right endpoint approximation. Now, if you look in the book in section 5.1, you'll see all these approximations for a specific function or functions, and they'll actually figure out the total area, numerically. Now, personally, I don't think you'll have to actually evaluate all of these, because just understanding that these are approximations is what's important, not the actual calculation, right? So try to understand these conceptually. So what happens if you do the right endpoint approximation? All right, so for the first interval, from here to here, my approximation point, or my x1 star, is right here, the right endpoint of the first subinterval. So I evaluate the function right here, and then, oops, what happened to my color? Here, okay. So my first rectangle is going to be that one. For the second one, again, I'm going to take the right endpoint of the second subinterval, evaluate the function there. That would be the height of the second rectangle. So that's that. For the third one, it's right here. So this one is going to be maybe slightly an overestimate. And for this one, it's 1, 2, 3, 4. The fourth one, I picked the right endpoint for the fourth subinterval. So I evaluate the function here. That would be the height of my rectangle. And so that is my rectangle. And then last one, I take the right endpoint, which happens to be B, and then that would be the height. And so you get this rectangle. If you add up all the areas, all 5 areas of the 5 rectangles, you get the right endpoint approximation, which will probably be bigger. Just by looking at the picture, this will be a bigger approximation number than the first one. All right. Where else can you do it if you don't have the right and left hand? Okay. It turns out you can just pick any point. All right. Maybe another nice way to do that is a midpoint. Okay. But it doesn't have to be. And in fact, you don't even have to pick a specific thing for each one. You can pick like a random thing, like, just pick halfway, for the first one, maybe the right endpoint for the second one, and maybe 1/3 of the way of the third one, or whatever. Okay, but these three, the left endpoint, right endpoint, and the midpoint approximations, these are sort of used as examples for illustrating this whole idea of the concept of the Riemann sum. Okay. By the way, the Riemann, it's not Riemann. Okay, German reading. Riemann sum is what this is called. The Riemann sum, a Riemann sum, is basically the total sum of the total area of the rectangular regions, where each rectangle has this height, which is f, evaluated at xi star, and the representative point of the ith subinterval, times the base of the rectangle, which is delta x, which is basically the length of the subinterval, each subinterval, if the partition is regular. By the mid one, if you evaluate each rectangle at its midpoint, so the midpoint of the first one, let me see if I can do this here. The midpoint of the first one will be right here. So you evaluate here. My rectangle will be that. Second one, you evaluate here. So the height will be here. This is a little harder to draw. Okay, but you evaluate here. So the height will be somewhere here like that. Oh, what happened? I lost my rectangle. Yeah, so something like this for the second one. This seems to be about the midpoint. So my third rectangle will be like this. Fourth one, here is the midpoint. So the fourth rectangle is like that. And the last one is going to be evaluated right here. And so this is my rectangular picture, or the approximation based on the midpoint of each. Okay. Now, which one is more accurate? Well, I should happily say it doesn't really matter. All of these are approximations. Sometimes the right hand is better. Sometimes the left hand is going to give you the better approximation. Sometimes the midpoint. Okay, but all of these are these are just 3 examples of what is called the Riemann sum. So in general, okay, let me just write down this thing here. A Riemann sum of F on AB is the sum from I to I is equal to 1 to n of F of X I star. And if you don't have regular partition, which means that maybe the delta X is going to be different. Maybe each subinterval is of different length. The first one being delta X1, the second the subinterval being delta X2 length, and so on. Then you can also vary these. And so this will give you the same thing, right? So here I am saying A is X naught, which is less than X1. These will define the partition. You have the n subintervals, the last xn being B, right? And xi star is in where? Okay, it's xi minus 1, xi. So this is the ith subinterval. Okay, and you can use this as a definition of a Riemann sum if you like. Notice here though, Riemann sum, there's no one Riemann sum, right? I mean, here we saw 3 Riemann sums, one for the left endpoint, one with the right endpoint, and one in the midpoint of each subinterval. So the Riemann sum heavily depends on the partition, which is defined by these numbers, and also where you pick the representative point for each of the subintervals, and n. Okay, so I mean the Riemann sum could have a variety of answers, values, and so that's what this Riemann sum is. So that's a you can use this as a definition of a Riemann sum. All right, good. So the area A under F on this interval is, what is that? It's approximated by the Riemann sum, which is again 1 to n of F x1 star delta xi. All right, and so how do you make this more accurate? For accuracy, more precision, we let n go to infinity. Or, I mean, if this is true, this is enough if you have a regular partition, right? If you have a regular partition as n, so because if it's a regular partition, which means each subinterval is of the same length, so the more you have, the smaller each subinterval gets. Right? If you don't have a regular partition, just say some of the partitions bigger than others, increasing n to infinity doesn't really do the job, because one of these or 3 of these subintervals can stay big and all the other ones can get smaller and smaller. Right? So what you can do is you will do the or maximum value of delta xi. So this will be the biggest subinterval. The length of the biggest subinterval approach 0. That would be the more accurate way of saying this. So we define the area I'm almost getting into the second idea here. The area, the second section. The area is going to be the limit of this Riemann sum. And I'm going to use a general case where we don't require the subintervals all to have the same length. Okay, the limit of this as the maximum delta xi approaches 0. Okay, so that's the area under the curve. All right, now I didn't do any calculations here. If you want to see the precise numbers for all of these, and if you want to see, you know, the numbers, the numerical computations, you can look in the book. I personally don't think it's necessary for you to have to calculate any of these things. I really, really want you to understand the concept of this Riemann sum, because it is a very clever idea. You start with a partition, you pick a representative point for each partition, you evaluate the function at each of these representative points, which will of course give you the height of each rectangle. And then you multiply each rectangle with the length, the base, the length of the subinterval, which is the base. And then you add up all of these areas. So the areas of those n rectangular regions, and that is an representative, or that is an approximation of the total area. And as you take the limit, as the largest of these subintervals become 0, which means all the subintervals become smaller and smaller, that limit, if it exists, is the area under the curve, as long as f is non-negative on AB. All right, so with that, I think we can go on to section 5.2 next time. Great.